If you have a computer or a smartphone, take that out and download the slides now. So today involves sorting algorithms. We'll be doing some of them and also talking about what they are and how they work. This is first a little refresher on what these things are, some examples of them and why we would use them, some theory and of how sorting algorithms work, and what nomenclature I'll be using to explain how they work. And then 3 examples of sorting algorithms. We will actually do these on the whiteboard, with you controlling the actions performed for this lecture. So there will be code, and we will be telling you what to do when we're sorting a list as a group activity. And then of course some exercises and additional learning materials as always. Any questions on the content of this lecture so far? Okay, good, let's get going. So, sorting algorithms sort of things. This becomes a complete surprise to you, but it's actually basically what we do. The thing is that this is often expensive computationally, so when we create these algorithms, or when people more clever than me create these algorithms, it's often a trade-off between simplicity in implementation and speed. And the faster it is, the more complex it is still, usually. Fortunately, these days, we have, in most libraries, have existing sorting algorithms implemented that are fairly complex. We'll spend time on this. So you generally don't have to worry about deploying these, but it's a good exercise for you guys to understand algorithms and for you to understand what's happening in the back end of your code. So, some theory first. So sorting is basically putting things in a certain order. We'll be working with numbers today, which means that the order is obvious, right? We just want to sort the numbers in order. But we could have some other metric. Maybe we want to sort tankers by number of liters of oil carried, or pigeons by number of feathers, or some other metric that we decided. Could also be that we sort things alphabetically, for example. Now we usually discuss sorting in terms of in place or not in place. So if we do in place sorting, we simply transform an existing collection of something. So an existing list of integers or an existing list of baseball players. And we change these in place, so we don't actually create a new data structure to do this. A not-in-place algorithm, it requires some new structure that we put these in. So we take the things, we copy the things out of our first thing and put them in another thing. As you may remember from previous lectures, this will may require some deep copy and stuff like that. So we're not doing that here. We're just doing in-place algorithms today. But keep in mind that there are some cases where you do sort not in place. So the purpose of it is basically probably that we have a list looking like this: 2, 3, 1, 5, 4, and 1, 2, 1, 2, 5. For some reason, say this is something we commonly use in most software. Right? At some point, you will need to sort something according to some metric. Not necessarily numbers, but maybe distance. And it's used in games quite a lot. If we have a scoring system, the obvious case is like finding a winner of the game. We just sort them and take the first element of that list. But it could also be something like if we're doing traversal across the world using, say, A*, we can sort the list to find the nodes that are cheapest first. So if you want to sort of rank nodes based on how cheap it is to traverse them, and then consider their viability in our search algorithm from there. You know that gets settled before I continue. So it's a very common use case for most software, and something that you will encounter at some point in your search. For example, if you do collision detection with mouse clicking you usually raycast into a 3D world, right? To find all the objects that are under that mouse click. Well, that would give you a list that you may need to sort that based on some metric, say the relevance of the object based on how much health it gives back. Or if we have a prioritization where we add health before we do damage, for example, we need to sort that way and then just process the list. There are many ways to skin this particular cat, and all of them have their own way. We'll see 3 ways today, and we'll practice 2 ways. But generally, we take a value from a list and compare it to 1 or more items in the same list and just put it where it's supposed to be. And this will give us some level of order. As with most computer science subjects, optimization here is a primary concern. And even today we do a lot of research on this. So there are whole fields dedicated to researching how we make sorting as efficient as possible. Should be noted, because this shows up because a student last year asked me about the sort. There are non-comparison sorting algorithms. Putting things into trees could be classified as that. So we're not really comparing stuff as much as we are just tossing it in there. We're not covering those in this course because they are magical and special. We're doing standardized, just normal sorting. Okay, so some examples of sorting algorithms. This is where I'd ask you to get your laptops out and find the slides on the web or in the, to get ready for that. So in Slack or on the web. So there's basically what we could call my first sorting algorithm. It's insertion sort. It's very simple, it's very easy to run, and it works well for fairly small data sets. So if we're using a couple of 100 items in a list, it'll work fairly well. It does not scale. And that means that if you have longer lists, you want something that's not insertion sort. Funnily enough, insertion sort performs very well. It's very fast. We'll just run through it if the list is already sorted. Now you'd think that, well, the list is already sorted. Why are we running a sorting algorithm? This shouldn't be a problem, right? Well, many other algorithms, quicksort that we'll see, for example, needs to run a fairly complex operation to determine if the list is already sorted. So this actually matters that it's fast on an already sorted list. We accidentally have this edge case, but maybe we accidentally sorted something twice. Because we're bugging a program, or we just happen to get sorted stuff. So insertion sort is actually fast. But we're all sorted. I hope the sound works. This is leftovers from this is something that was produced by a European Union project, where some of the best tax money spent ever, where they turned sorting algorithms into folk debts, which we will now use as teaching